Hey, today we're going to talk about evaluating polynomials, which are functions that look like f of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus, and we kind of just go on down to a sub 1 x plus a sub 0 x to the 0, which is 1. So we just get a sub 0. And I'm going to write this in sigma notation because I'll use that to point out two useful things. And we'll write it as k is equal to 0 to n. So this is your dummy index going from 0, 1, 2, 3 up to n, a sub k, x to the k. So sigma notation gets a lot of bad rap, but it is useful because it'll show us a really easy evaluation point. But we're going to start by asking, what's the obvious one? F of 0. Ooh, lightning. And what we get is when we plug in 0, we get a sub n x to the 0. Well, that's just 0 because x is 0. 0, 0, all the way down until you get to a sub 0. And all you get is the constant. So if you plug in 0, you get the constant. This is a point that evaluates on the polynomial 0, comma, a sub 0. If you're graphing it, this is just a freebie point. And you also get 1 because look at the sigma notation. This is just the sum of a sub k times 1 to the k. This is just the sum a sub k. K equals 1, not 1, 0 to n. It's just the sum of the coefficients. And we also get, well, before I show you negative 1, think about that. This one is 1 comma the sum ak, which is a little bit less pretty than, just it's this number. But this is an easy point to find on the graph as well. And finally, I'll not write this as a point on the graph, but we go k equals 0 to n ak negative 1 to the k. Because we're just plugging in negative 1 for x. And what that shows you is it's actually, I'm going to write it backwards, a sub 0 minus a sub 1 plus a sub 2 minus, got a plus in there somewhere, and we'll write it as plus negative 1 to the n a sub n. So this is just adding and subtracting the coefficients, alternating sign, starting at the constant, subtract, add. So these are 3 points on the polynomial that are pretty easy to find. But what if you want to find other points? Like what if you have a proposed 0? Well, that's where division comes in. And what's interesting here is division is at its heart a way of taking a function f of x and rewriting it as some quotient of x times some divisor, and I'll call the divisor g of x, plus a remainder of x, where the degree of the remainder is strictly less than the degree of the divisor of g. So just so you know what I'm talking about, this is what is f of x over g of x, or g. Now, one of the things you can do here is what if g of x is equal to x minus a? That is a really useful pick of this g, because then it says f of x is equal to q of x times x minus a plus some remainder of x, where the degree of the remainder is less than the degree of x minus a, but the degree of x minus a is 1, which means the degree of the remainder is 0. So this is constant. So it's a constant, a remainder. And that means f of a is equal to q of x times 0, because x minus a, well, if x is a, that's just 0, plus the remainder, which I'm going to drop the x off of it because it's constant, plus this number here. So what this says, f of a is equal to the remainder. So if you want to evaluate a polynomial at any point, you just divide it by x minus a. So that gives you a point on the polynomial, a comma the remainder. So this is a really handy thing to do, except if you're trying to do this with long division, it's kind of tedious. This is why synthetic division is super handy. You can evaluate polynomials without having to take the point you're trying to evaluate at to the end. So in the next video, I'll show you how to do polynomial synthetic division. Anyway, thanks for watching. See you next time.